So good morning one and all. So let us start today's class. So now today we'll discuss a multiplexing technique that is called time division multiplexing. So previously we have discussed about frequency division multiplexing. So now let us see what is TDM. So here we transmit multiple number of signals one after another through the same channel. So that is called TDM. What we do? We transmit multiple number of signals through the same channel one after another. So in the last class we have seen FDM, frequency division multiplexing. There what we have done? So we have transmitted multiple number of signals by sharing the channel. Okay, what you have done? So we have modulated this to some frequency fc1, so these to some another frequency fc2. So let us take one more signal. So this is modulated to another frequency fc3. Now here we have divided the entire bandwidth among the users. Okay, so we are transmitted simultaneously by dividing in the bandwidth. Okay, so they have occupied the different set of frequencies and they have modulated to different carrier frequencies. This is FDM. But in TDM what we do? So we transmit at the same frequency but one after another at different times. So so in FDM, so the sharing of the channel is done on the basis of frequency. Frequency is shared among the users or among the signals. In TDM, what happens? So the sharing of the channel is done on the basis of time. The users will share the time. Okay. Now I will let you know this later. Now, so here how it happens? Now let us take this example. So here, so we have 4 users, 1, 2, 3, 4. So here they have been transmitted along the same path or along the same channel at the same frequency, but at different times. What will happen? So we allocate a time slot to each user. First what we do? First let us take user 1. We transmit the first alphabet. Next, from user 2, we transmit the first alphabet, that is B. From user 3, we transmit C. From user 4, we transmit D. One after another. Okay. So we are sharing the time. Correct? So what happened here? First, we transmitted A, next B, next C, next D. Okay. So we completed one alphabet from each user. Next, what do we do? Again, we go for second alphabet of user 1, user 2, user 3, user 4. Okay, so we are transmitting one after another along the same channel at the same frequency but at different times. So here we allocate time slot to each user. During that time slot he can use the channel. Okay, so the entire bandwidth is utilized for a short period of time by each user. So in this way we are able to transmit multiple number of signals through the same channel by sharing the time. Now we do demultiplexing, obviously reverse. We take A here, okay, next B here, next C here, next D here. So we do reverse of that multiplexing, that is called demultiplexing. Okay, right. So to implement this concept we use this, that is called time division multiplexing. Here so here we are multiplexing n number of signals. How many signals we are multiplexing? N number. In general we take n number of signals are to be multiplexed. Here we have low pass filters which removes unwanted high frequency components. Now we have something called commutator. What do we have? Commutator. Okay, so it is a high speed switching circuitry. It's a high speed switching circuitry. So it rotates like this. Okay. Now, so here, what is the job of this commutator? Okay, it will collect the samples from each and every signal. Okay, so it makes a rotation. Suppose what happens here is, suppose by the time it makes one complete cycle, it will collect sample from each of the n signals. Okay, I will explain later. Now here, after that, so they will be modulated and they will be transmitted over a channel. So they will be demodulated, and at the receiver side we have a reverse of the commutator, that is called decommutator. Okay, so obviously it will do the reverse operation, and finally again we have low pass filters for reconstruction, and these are the outputs. Okay, now here this commutator at the transmitter side and the decommutator at the receiver side should be synchronized. Okay, now so let us see how this will happen. So this commutator is a high speed switching circuitry which collects samples alternatively from each signal. Okay, it completes one cycle. By the time it completes one cycle, it collects one sample from each of the n signals which are to be multiplexed. Okay, how it happens? Okay, so let me take an example. Now let us take an example here. So here these are the three signals which I want to multiplex. What kind of multiplexing? Time division multiplexing. Okay, so I have taken samples actually. What a signal? Actual signal is something like this. That is being sampled. This is another signal. This is another signal. So they have been sampled, and these are the samples. Now, so after sampling, so actually TDM is the application of sampling. So what happens if a sample signal, there is a free time between any two successive samples. Time is freed up. So it's a conservation of time. TDM is all about conservation of time. You can observe between any two samples we have some gap. The time is free. So in that free time we can transmit some other signals. That is simple logic. Okay. So why to keep the channel free? So in that gap, let us transmit some other samples which belongs to some other signal. Okay, so that is the basic idea of TDM. So here between 1 and 2, okay, there are no samples, the time is free. I can use that free time to transmit some other samples. Now here, so actually I will take some offset. Let us take the sample is somewhere here. I have shown here, but let us take this red sample is somewhere here. Okay, let me take another color. So let us take this red sample is somewhere here. Okay, so let us take this green sample is somewhere here. Okay, now what will happen? So between 1 and 2, I can transmit these three samples without overlapping. A blue color one, a red one, and green one. Okay, now so that is simply TDM. Okay, so what I do is, since there is a time gap between any two successive samples, in that gap I will transmit some other samples. So what I do is, I will transmit these three samples, these three first samples. Okay, what I do is, I have transmitted these three first samples. They belong to three different signals. This is the first signal, this second signal, this third signal. Okay, so I have taken the first samples of all three signals. Okay, next I will take the second samples of all signals. Where are they? So these three are the second samples. Obviously, next these three are the third samples. These are the fourth samples, so on and so on. Okay, so what is the job of the commutator? It will collect the samples alternatively from each signal. So by the time it completes one cycle, it will collect 3 samples belong to 3 different signals. Okay, so the commutator will collect these 3 samples by the time it completes one cycle. The next cycle it will collect these 3 samples. In the third cycle it will collect these 3 samples. In the fourth cycle it will collect these 3 samples, so on so on. So by the time it completes one rotation, it will collect one sample from each signal. Okay, now so here what is the time duration? It completes one cycle in every TS seconds, which means in every TS seconds we are transmitting 3 samples. Okay, but in general, so here what you have taken, we are multiplexing n signals, no? So that's why, which means this commutator will collect n samples by the time it completes one rotation. Means in TS seconds it completes or it transmits n samples. Okay, n samples in TS seconds. But you know already these are only samples, so they will be quantized, they will be encoded. Okay, so n samples, but how many bits? N into n bits. In how many seconds? TS seconds. So what is the bit rate? Actually what the bit rate means? The number of bits per unit time. Okay, obviously we are transmitting n into capital N over how many seconds? TS seconds. So this is a bit rate. Okay, that is RB. N by TS, or also you can also write what is 1 by TS? Fs. So this also can be written as n into Fs. Okay, now so what advantage? What advantage here? So if you transmit directly, you could able to transmit only any one of these 3 signals. But with the help of TDM, we are transmitting 3 signals during the same time interval. Okay, so you observe these 3. These 3 are multiplexed. How they are multiplexed? So here simply, so there is a gap now. In that gap I am transmitting one red signal and one green signal. Here is again gap. I am transmitting one red signal and one green signal. Here gap. I am transmitting one red signal, one green signal. So I am effectively utilizing the time. Obviously within the same time I could able to transmit all 3 signals with help of TDM. Okay, now so this is about TDM. Yeah, so it is more suitable for digital modulations, whereas FDM is more suitable for analog modulation. Okay, so the another example. So I have taken 3 signals. So one is something sine wave. This is sine wave. This is a triangle. Yeah, so I have multiplexed. This is TDM. You can see here, right? So this is a sine wave. This is the triangle. Okay, so within the same time I could able to transmit 2 signals by sharing the time one after another. Okay, this is a TDM signal. So this is a recovered signal after recovery. These are some problems, you solve them. Right, so with this we complete TDM also. Okay, you remember these formulas, very important. So one more thing I forgot to tell you is, so this is called a frame. What is called a frame? In a frame we are transmitting 3 samples. So if you remember, every TS seconds the commutator will complete one cycle, no? So in this time we are transmitting 3 signals, right? 3 samples. Okay, now so during TS seconds, right? So this is called frame. In a frame In every frame we are transmitting 3 samples. So why 3? Because here I have taken only for example, but in general here it should be n number of samples. Okay. So what is small n? It is encoding capacity. The small n is encoding capacity. What is capital N? The number of signals that are being multiplexed. Okay. Now, so that is about TDM. Now, so let us move on to the. So now I give some introduction to the digital modulations. You know already in digital we transmit symbols. Okay. So suppose if I say m equal to 2, that means binary. Okay. What are the binary digits? It can be only 2 types. Binary means we have only 2 different symbols. What are they? Either 0 or 1. This is binary data. We call it the binary data, right? You transmit either 0 or 1. So these are only 2 distinct symbols we have. Okay. Now source. This source will give some data or symbols. We call them as MI. Okay. MI is a data. So why I am writing MI? Because here suppose for what the first symbol 0, what is second symbol 1. Okay, because in binary case these are only 2 possible symbols, 0 or 1. Here, so from the source you may get 1 or 0. So the first symbol is what you have written 0, second symbol is 1. Okay. Now, so these symbols will be modulated. How they are modulated? They will be modulated digitally. After modulation, so this M1, that is 0, that is represented by S1 of t. M2, that is represented by S2 of t. So simply what will happen here is, so this source will give some symbols after like M1, M2, so on, Mn. How many symbols? Let us take M1, M2, so on, MM. These many symbols are emitted or generated by the source. Now this will be modulated digitally. After modulation, what is the, how to represent them? Like S1 of t, S2 of t, so on, Sm of t. These are the M modulated waveforms. Okay. Okay. Now here one more thing you must know is, so the source will emit or generates data for each and every time. Suppose you might be aware of this in your courses at least. Suppose how to write this 0 and 1. 0, let me write 0 as -1. Otherwise, let me take 0, this is 1. Okay, so this is -1, that is 0. This is 1, that is +1. Okay, now so there is something called time duration or bit duration. Okay, so for every t seconds you get a bit or you get a symbol. Okay, so this is another time t. So the source will emit or generate symbols every t seconds. Okay, suppose you will write the data like this, no? So if I ask you to draw the waveform of the data, what do you write? Suppose if I write like this. Okay, suppose this is 1, 0, 0, 1, 1, 1. So obviously you must define the time duration. This is t. Every t seconds one symbol is emitted or generated. Okay, so after modulation they will be represented with this S1 of t, so on, Sm of t. Okay, now so we transmit over a channel. So this is a receiver. What you receive is x of t. Obviously what is x of t? That is corrupted version of Si of t, that is Si of t say plus some noise n of t. We'll discuss everything about receiver later, but for time being, just remember this. So these are the symbols, and this is the modulated waveforms, which is done in the digital domain. Okay. Now, so here, so let us go for very important, that is called signal space analysis. What is that? Signal space analysis. It is very important, which means we are analyzing the signals in the space. Okay. So it is a very significant role in digital communications. Yes. Okay. Now, so first of all, let us go with a geometrical representation of a signal. Here in digital communication, so we must use geometry. Okay. So with geometry only we can able to find out the behavior of the modulation techniques in the presence of noise. So that's why I want to give the introduction to the geometry of the signals. You might be aware of geometry anyway, but so here let us study the signal geometry. Now, so just now I told you we have a set of M energy signals. Where are they? These are the set of M energy signals. How many are there? M number of signals are there. Actually, what are they? They are the modulated waveforms. These are set of M energy signals. What is M? M is the number of distinct symbols. Here you should not say symbols. They are distinct symbols. Why? Because here how many symbols are there? 1, 2, 3, 4, 5, 6. But how many are distinct? Only 2. Because they are repeating, no? See, we have 1 year, 1 year, 1 year, 1 year. Year 0, 0. So the distinct symbols are only 2. Okay, they will be repeating. So the same symbols will be repeating because there are only 2 different possibilities. Okay, so M represents the number of distinct symbols, not the symbols, the number of distinct symbols. If it is binary, obviously 0 and 1. If it is quaternary, so obviously if M equal to 4, what are the possible codes? You know already. What are they? 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 possible distinct symbols. But here each symbol will have a 2 bits. Each symbol has got 2 bits. Here symbol has got only 1 bit. Okay, you know already. If M equal to 8, what will happen? 000 to 111. Each symbol will have a 3 bits. So we'll discuss about everything later. Okay, so M is the number of distinct symbols, and after modulating them, you get a set of M energy signals. So they are called S1 of t, S2 of t, so on, so on, Sm of t. Now, so here what I have written, those set of energy signals can be represented as a linear combination of n orthonormal basis functions. Okay, so don't get confused with these things. What I want to say is, these signals, M energy signals, so on, Sm of t, can be represented as a linear combination of what? Basis functions. What are the basis functions? Phi 1 of t, phi 2 of t, so on, what? Phi n of t. Okay, so these set of M energy signals will be represented as a linear combination of n basis functions. Please remember, here the number of energy signals are M in number, the number of basis functions are n in number. So what is the relation between M and n? The relation is M is always greater than or equal to n. Very important. Okay, so what I want to say simply, what is the linear combination? First of all, suppose if I write y equal to a1 x1 plus a2 x2 plus so on an xn. What you can say about this? Here y is a linear combination of x1, x2, so on, xn. Okay. What about this a1, a2, a2? They are the coefficients. Okay. The same way, so what I want to write here is, here those set of m energy signals, that is S1 of t, S2 of t, Sm of t, they can be written as linear combination of basis functions. What are the basis functions? Phi1 of t, phi2 of t, so on, and phi n of t. M energy signals can be represented as a linear combination of n number of basis functions, phi1 of t, phi2 of t, phi n of t. So what will happen? Obviously, so S1 of t, what do I write? S11 phi1 of t plus S12 phi2 of t plus so on plus S and 1n phi n of t. Here what I have written? S1 of t is a linear combination of phi1 of t, phi2 of t, phi n of t. Obviously, these are the coefficients of expansion S11, S12, S1n. Okay. Now, if you write for second signal, what is S2 of t? Obviously, what do you write now? This is S11. So, please understand the notation. S1 of t, S11, S12, S1n. Okay. S2 of t, what do you write? S21, phi1 of t. You understanding my point? S22, phi2 of t plus so on. What is the final one? S2n phi n of t. Obviously, S2 of t is written as a linear combination of n basis functions. So these are the coefficients of expansion. In general, here we have two things. M number of energy signals, let us take I, varies from 1 to m. Now n number of basis functions, j, varies from 1 to n. Okay. Now what do you write about these things? So what do you write? Si of t equal to summation Sij phi j of t. J varies from 1 to n, I varies from 1 to m. So this is the final expression. What is Sij? The coefficient of expansion. Okay. So this same thing I have written here, no? Yeah. So I forgot to mention 0 to t. Obviously, every Si of t exists only from 0 to t. In the sense, only duration of time. So all these will exist from 0 less than t less than capital T. Okay. What is the t? Symbol duration. Now, so how to find out these coefficient of expansion? Sij. They are simply constant, no? They are coordinates, something like coordinates. Okay. Sij. How to find Sij? Integration 0 to t Si of t phi j of t dt. Suppose if I ask you what is S11, which means I equal to 1, j also equal to 1, that is S1 of t into phi 1 of t dt, integration 0 to capital T. Okay. In this way you would find out the coefficients of expansion. I varies from 1, 2, 3 up to m, j varies from 1 to 3 up to n. Okay. Now, so about this next, yeah. So now this can be this can practically implemented like this. Here, what is happening here? What happened here? Just now written here. What is SI of t? Si1 phi1 of t plus si2 phi2 of t, so on so on, sin phi n of t. It is from this expression only. If you expand this summation, what do you get? Si of t equal to j varies from 1 to n. Si1 phi1 of t plus si2 phi2 of t, so on so on, sin phi n of t. I varies from 1 to m. Okay. So same thing I have written here. So this is what we have written. Si1 into phi1 of t. Here what do you get? Si1 into phi1 of t. Here what do you get? Si2 into phi2 of t. So on so on. Finally sin into phi n of t. So what exactly is this? Si1 into phi1 of t plus si2 into phi2 of t, so on plus sin into phi n of t. Okay. Here what is varying? J is varying. From where to where? 1, 2 up to n. So that's why you can take summation j equal to 1 to n Sij phi j of t. This actually what is this? This is Si of t. Okay. Now actually this is similar to the modulator actually. Why? Because what is Si of t? I told you they are the set of modulated signals, S1 of t, S2 of t, so on so on, Sm of t. So they are generating Si of t. It is similar to the modulator. Okay, I will discuss everything later. But why? Because here these are multiplied with some carrier, something like carrier, phi1 of t, phi2 of t, phi n of t. Okay, this is a message signal. This is a carrier. They are being multiplied. Okay, it is similar to the modulator. Okay. Now anyway, so it is called synthesizer. It is called synthesizer. Okay. Right. So let us get into the inner product or dot product. You might be aware of these products, inner product or also called as dot product. We denote like this. X comma y means it is a dot product of two vectors. You know the dot product, how to find dot product of a vector. Okay. Now here, so these basis functions, how many are there? N in number. Okay. But as I told you, they are real valued functions. Not only that, they are orthonormal. Very, very important. All these basis functions just now mentioned are, all these should be real valued. Along with that, they are orthonormal. You might have heard about orthogonality. Okay, what is orthonormality? So orthonormality means orthogonality plus unit energy. Okay, orthogonality plus unit energy will lead to orthonormality, which means all these basis functions are orthonormal, which means they are orthogonal to each other. All these basis functions, n number of basis functions, are orthogonal with respect to each other. Not only that, they have a unit energy. Okay. Now, so what I want to say is, all these basis functions, phi1, phi2, so on, phi n, they are orthonormal, which means they are orthogonal with respect to each other, which means phi1 of t is orthogonal to remaining basis functions, phi2 of t is orthogonal to remaining basis functions. So each and every basis function 2 is orthogonal to remaining basis functions. Okay. Along with that, each and every basis function has unit energy. then they're called orthonormal. So obviously, so if I say what is this inner product of phi1 phi2, if it is 0, obviously phi1 and phi2 are said to be orthogonal. If the inner product is 0, they are said to be orthogonal. Okay. So what is the inner product of the vector with itself? Can you tell me this? What is inner product of a vector with itself? Actually, it is nothing but energy. Okay. So what exactly I want to say is here. So what is inner product of phi I, phi j? How to write this? So I am writing in the form of signals only. You can write in the form of vectors also, but what exactly happens here is, suppose if I say phi1 phi2, what's inner product? If they are signals, what do you find out? It is 0 to t phi1 of t into phi2 of t dt. Okay. Specifically, if I take phi I and phi j, I want to find out the inner product of these two. Obviously, what do you do? 0 to t phi I of t into phi j of t dt. So obviously, so what I written here? If I equal to j, okay, if I is not equal to j, they are 0, which means phi I and phi j are orthogonal first. If I equal to j, obviously they are same. If I equal to j means what? The inner product of a signal with itself. What it becomes? Phi I of t, integration 0 to t, phi I of t, phi I of t. That is phi I of t whole square. What is this represents? Energy of the phi I of t. That equal to 1. Are you getting my point or not? Okay. So this statement is enough for the orthonormality. Okay. So they are orthogonal. Not only that, they have unit energy. Each and every basis function should have unit energy, and it should be orthogonal to with respect to other basis functions. Simple logic. Okay. So in the simplest form, what you can say? So integration 0 to t phi I of t phi j of t dt should be, so I am just taking two basis functions, phi I of t, phi j of t, random basis functions. So if they are 1, if I equal to j, if I equal to j means what? We are just finding energy. Why? Because if I equal to j, what happens? Phi I of t whole square dt, that is energy, right? 0 if I is not equal to j. If I is not equal to j means we are taking the integration of product of two different basis functions. If that is 0, obviously they are orthogonal. It is for orthogonality. The second line is for orthogonality. It is for unit energy. If these two are satisfied, it is said to be orthonormal. Right? So all the basis functions should be orthonormal. That is simple logic. Correct? Now here, so we had this coefficient, no? In the expansion, we had the coefficients. What are they? Si1, si2 or s11, s12. These are the coefficient of expansion, or simply Sijs. These are the coefficients of expansion. Now they can be written in the vector form. Okay. Sij are naturally viewed as n-dimensional vector denoted by Sa. Okay. So what I want to say is here, so we are writing this expression is there, no? You must remember these two expressions. Si of t equal to summation j equal to 1 to n Sij phi j of t. So I varies from 1 to m, that is obviously you must remember. And reverse, what is that? What is Sij? formula is 0 to t, integration 0 to t, si of t, phi j of t dt. These are the two things you must remember. Okay. So it is called synthesis. It is called analysis. Now here, so in this, what are the Sijs? They are called the coefficients of expansion. Okay. Now, so these can be written, these coefficients can be written in the vector form. Okay. So how? Now, so Si of t, these vectors, these coefficients Sijs can be written in the vector form. In the vector form denoted by Si, vector Si. Now remember, this Si has one-to-one relation with Si of t. This Si has one-to-one relation with Si of t. What do you mean by this relation? If you know Si's, it exactly means that you know Si of t, and vice versa. So if you know Si of t, which means you have complete information about Si of t, or vice versa. What is Si? It is a vector which contains the coefficients. What are the coefficients? Sijs. Okay. Now here, so let us see. This is the Si. Actually, it's a vector. Vector means it is a column matrix. Okay. Now, all this, suppose, what is Si in the expansion? Just now I told you. But expansion, no? Yes. Let me go back. In the expansion, so Si. What are the coefficients of expansion? Si1, Si2, Sin. So on and Sin. They are written in the form of a matrix, column matrix. It is called a vector. What is vector Si? Simply, it contains the coefficients of expansion, that is Si1, Si2, so on, Sin. Obviously, what is the order? N cross 1. This is a column matrix called a vector. So I varies from 1 to m. You can change the I. Suppose, for example, what is the vector S1? It is a representation of S1 of t. What it contains? S11, S12, so on, S1n. What is S2 contains? S21, S22, S2n, so on. Like this, we have how many vectors will be there? Si is a vector, I varies from 1 to m, which means we have m vectors of order n cross 1. They are column matrix. Si is called signal vector. Okay. Now synthesizer. Now this is analyzer. So what analyzer? So since this is the analyzer. Okay. What happened here? Yeah. So how to get Si1? Okay, let me take Sij. What is that? 0 to t, Si of t, phi j of t dt. If you keep I equal to 1, this is S1, this is phi j of t dt. So that is, so if you want to get Si1, it is integration of Si1 equal to, j equal to 1. No, I'm sorry. Here I'm asking for j equal to 1. J equal to 1. So what is Si1? What is Si1? J equal to 1 means 0 to t Si of t phi 1 of t dt. In the same way, how to get Si2? How to get Si2? Obviously, integration 0 to t Si of t phi 2 of t dt. Okay. Now this is the analyzer. So how to get Si1? So Si of t into phi 1 of t, and this product is integrated over 0 to t. Okay. So here we have integrator 0 to t. Now what is being integrated? Si of t into phi 1 of t dt. Obviously this will be equal to Si1. Here what happened? Si2. Here what happened? Sit into phi 2 of t integration over 0 to t dt. This is Si2, so on and Sin. It is called analyzer. Okay. So what are they actually? We are representing these two equations. This is a synthesizer. This is analyzer. Okay. In this, keep j equal to 1. What will happen? Si1, that equal to integration 0 to t Si of t phi 1 of t. Keep j equal to 2. Obviously you get second one. So on so on. So the first equation is called synthesizer. This is synthesizer. The second one is called analyzer. So they are nothing but modulation and demodulation. They are more or less, this is a modulation. The first one is a modulation, second one is a demodulation. This is a broad idea. Okay. Now what advantage of representing as a vectors? We have written these vectors, no? S1, S2, so on, Sn. We have vectors S1, S2, so on, Sm. M vectors. So why to represent them as a vectors? Because so you can represent these vectors in a space. Okay. Space means geometrical space. Suppose you take x comma y, no? So this is a point, right? There's a point. So it's nothing but a vector. So it is called space. Okay. We can represent all these vectors in a space, geometrical space. So I will let you know all these things a little bit later. Now we may visualize set of say vectors as a set of m points in n-dimensional Euclidean space with n mutually perpendicular axes labeled as phi 1, phi 2, phi n. This n-dimensional Euclidean space is called as a signal space. It is very, very significant to represent these signal vectors in a space. It's very, very important. Okay. So finally what I want to say is simply I want to say this. So we have S1 of t, S2 of t, so on, Sm of t. These are set of m energy signals. They have been represented as a linear combination of basis functions. So their m in number, their n in number. So their energy signals, these are called what they are called? Basis functions. How are they? They are orthonormal. Okay. So all these S1 of t, S2 of t, Sm of t have been represented as a linear combination of this n basis function with the coefficients of expansion Sij. That is very clear. Now, so for this S1 of t, all those things we had vectors. Okay, suppose we have vectors s1, s2. What is s1 vector? It contains how many elements? It is a column matrix, that is s11, s12, so on, so on, s11. So for each and every signal s1 of t, so si of t is a s1 of t and s1, they have a one-to-one relation, which means they are exactly same. So for each and every s1 of t, suppose we have vector s1. For this, what is the vector? s2. For this, what is the vector? sn. Okay, we have vectors. What are the dimensions of the vectors? I mean this matrix n cross 1. We have a m vectors whose dimensions is n by 1 or n cross 1. What is n? The number of basis functions. What is m? The number of signals. What is the relation between these two? M is always more than or equal to n. I will let you know why it is so a little bit later. But here what is the logic is, I want to represent these vectors in a signal space. Signal space means geometrically. Okay. So, but we have to mention what is the dimensionality of the geometry. What is dimensionality? N-dimensional. Why is it n-dimensional? Because suppose if you take the geometry, you must need axis, right? Suppose if I say two-dimensional, generally what axis? X and Y. If I say three-dimensional, I need one more axis. If I four-dimensional, I need one more axis. Okay. So the dimensionality of the geometry depends upon the number of axes. Here, n-dimensional means we need n axes. What are the axes? These are the axes. They will act as a axis. Why they act as axis? Because they are orthonormal. Actually, all the axes should be mutually perpendicular to each other. Don't you think so? X axis, Y axis, obviously they should be perpendicular to each other. That is, they should be orthogonal to each other. Okay, and not only that, they have a unit energy. So because of this property, these basis functions will act as an axis. Since we have n basis functions, it should be n-dimensional geometrical space. Okay. Now these m signals will be represented in this n-dimensional space with a point. Okay, what I want to say is simple. Now, so since we have a n number of basis functions, they will act as axis. Suppose let us take only two basis functions are there. Let me take here only two are there, which means it is a two-dimensional signal space. We call it the signal space. So here, what is the axis? Not x and y. What are they? Phi 1, phi 2. Don't write t here. Just phi 1, phi 2. Okay. It is a two-dimensional signal space. It is a two-dimensional signal space. Now, in the signal space, you can denote all these vectors like with a point. Suppose if I write a point here, it can be s1, somewhere s2. Just like we represent normal geometrically, right? This is maybe another point s3. This is s4. So all those m signals can be represented with a point in a n-dimensional signal space, or it is also called as Euclidean space. So here it is a greater role in case of digital communications. So what we do here is we represent signals in a geometry. Not only signals, noise also. So we represent signal plus noise in a geometrical space. It is called signal space. Okay. So we stop here. Thank you.